reactions that have rearrangements, you need to be extremely careful. Again, I know I have said this before, but you need to practice your reactions with different starting materials. You need to remember the conditions of the reactions. And you need to remember whether the additions are Markovnikov or anti-Markovnikov. So let's start right here. This is the hydration of the double bond. I have water and I have a little bit of sulfuric acid in there. I like to draw my intermediate carbocation because I always check for possible rearrangements. So carbon number 1 right here has 2 hydrogens. Carbon number 2 right here, it has only 1 hydrogen. I check that because this addition is Markovnikov. So whenever you protonate, the hydrogen will go to carbon number 1 and the positive charge, the carbocation, will be on carbon number 2. Check what the neighbor has. The neighbor on the left is a primary carbon. That would be a terrible place to put a positive charge. But this one on the right side is a tertiary carbon. And that tertiary carbon happens to have a hydrogen attached to it. So that would be an easy group to move. So right here, secondary carbocation. If we have a hydride shift, the positive charge would go to this carbon and it would be a tertiary carbocation. Much better carbocation. So that's what we're going to have. We're going to have a hydride shift. So let me draw the hydrogen in orange. I know some of you don't like orange or pink. But it's now a much more stable tertiary carbocation. And now the water will attack and I'll end up with an OH on my tertiary carbon. So that was a hydride shift right there. Now the second reaction is the oxymercuration demercuration reaction. And this reaction right here, although it's Markovnikov, it will not have any rearrangements. It doesn't go through a carbocation intermediate, and that's why it doesn't go. It doesn't have rearrangements. So when you add the elements of water across the double bond, the hydrogen will go to carbon 1, the OH will go to carbon number 2. So I get a secondary carbocation, and I want you to notice the difference of these two. The first one, we did a hydration reaction, but we had a hydride shift, so we get a different backbone. This one, we're hydrating, but we know exactly where the elements of the water are going to end up attached because I have no rearrangements here. So I'm going to put that really big right here. No rearrangements. The last one, what's important about the last one? It's called a hydroboration oxidation reaction. And what have I said in class about this reaction in particular? Hopefully you are saying that it's one of only 2 anti-Markovnikov reactions. And this reaction doesn't have any rearrangements either. So it's opposite of Markovnikov and it doesn't have any rearrangements. So the hydrogen will go in this case to carbon number 2, so it'll be right here. The OH will go on carbon number 1, on the outside carbon. So make sure you practice these reactions. Again, there's no possibility of rearrangements, so I'm going to put it in here too. You need to know the mechanism of the reaction of all these 3 reactions because I'm also going to ask you about the stereochemistry of the additions. And this addition right here, although we cannot see it in this product, it's going to be a syn addition across the double bond. So the hydrogen and the OH that we added are going to be on the same side. Again, we cannot see it here, but if you use a cyclohexene, then you're going to see the hydrogen and the OH on the same side.